to the NPTEL course on storage systems. In the previous class, we were looking at some aspects relating to consistency, and we mentioned that consistency is connected with the consensus problem or the commit problem. So today we will take a look at the consistency management in storage systems, and I will get started with some aspects related to the commit protocols. So first of all, consistency management is critical both in single site storage systems as well as in multi-site storage systems. It's not just only the case that in multi-site storage systems I have to worry about it. Why is that? Because if I look even a single site storage system, that site itself has many components, and therefore the consistency problem could still be here also. To appreciate why that's the case, let's just take an example of a file system operation. All of you know that there is an operation called link in Unix, and basically it creates an additional link to a file. What is this particular command? ln/abc to /xy. What does it do? This is the source, this is the target. This is typically a directory, x/y is a directory, this is a file. That means that what the semantics of this is that the file C will have another name in this directory x/y. So in addition to the file being in ABC, there will be another file called /xyc. Okay. And basically what happens is that there is a link count that increases by 1. So it is essentially, you might call it as a way of referring to the same object through two different pointers. That's basically what is happening. Now, notice that if I want to do some operation like this, which is resistant to failures, it is not that trivial. Okay. Why is that the case? Let's think about what kind of things I have to do this operation. What is involved here? First of all, the file C, it has got a metadata, right? The metadata corresponding to C, right? And it keeps track of how many copies are there, right? So you have to increment what is called the link count of C. So it basically says that instead of it being present in only one place, it's now present in 2 places, okay? And the inode, there is only a single copy of the object. There's only a single copy, except there are 2 pointers. One from the directory /ab, that is the thing which is pointing to that C, and the directory xy, that also is pointing to C. So first of all, you have to, why do you need the link count? So that in case either party tries to delete it, so sorry, it is deleted from either part of either directory, you have to keep track of when to actually delete the file. For example, if I delete, after having done this link, if I delete /abc, there still should be /xyc, should still be there. Okay. Similarly, if I delete in x/x/yc, then this copy should still be there. So the link count keeps track of it. Okay. Then the next aspect of this is that I need to actually put the entry into the directory y, because now C also is going to be there in the directory y. Now if you think about it, these 2 operations 1 and 2, they are 2 updates to the storage system. When you increment link count of C, you are incrementing some field in the inode, which is a different place on the disk than when you add the entry C to the directory y. So these 2 are 2 different places on the disk. Okay. Now there is no magic by which you can update these 2 at the same time. Okay. Whatever method you think of, it requires some kind of let us say sequentially done. Even if you think of doing it simultaneously, it is a very complicated procedure, because you want to do it simultaneously, you need to do some time synchronization, and time synchronization is not possible within a few milliseconds accuracy, all kinds of things are there. So it turns out, if you think hard about the problem, it turns out it is impossible to do it in a safe manner simultaneously. It's just not possible. Okay. So in a sense, one has to precede the other. There is some kind of ordering that happens. Now there are two possible ways. Do I do 1 followed by 2 or 2 followed by 1? Now depending on which way you do it, if there is a failure, there are different consequences. In one case, you have what is called production of garbage. In the other one, what is called a dangling pointer. So depending on which one you do, you have one of these two possibilities. There is plenty why that's the case. Okay. Now typically, it's better to have garbage than dangling pointers. Okay. Dangling pointer means you are referring to something which doesn't exist. It is a more catastrophic error. Okay. Whereas having some garbage which nobody points to is a more safer thing. Okay. So here the idea here is, if I am trying to figure out whether to if I want to decide between 1 and 2, I will try to choose one of them which produces garbage rather than produces garbage. For example, suppose I go with 2 first. If I add entry C in directory Y, that means I am already pointing to some object, but I am not really linked it yet. Okay. I have still not done the job of actually linking it. Okay. And if there is a power failure or panic whatever, then that entry will be pointing to garbage. Basically all I have done is I put an entry into the directory, but it is not really pointing to because let's say that I flushed that part of it to disk, that is X by C, right. What I have done is that directory entry has been flushed to disk. So, but because of power failure, I have not been able to increment this part of it. So that means that there is a record in the system, persistent system, part of the system, that there is an entry in directory Y, but actually the link count has not been incremented. Okay. Whereas about other possibilities, if you increment the link count, that goes let us say flush to disk, and then you fail to update the entry in Y. Suppose there is a power failure in between, that is you increment this has gone to disk, but this has not yet gone to disk, it is still sitting in memory and it died once the power failure happened, it could not be flushed to disk, let us say. That means that when I delete C, right, what happens is that, now notice that because I did not add this one, there is actually exactly still only one place C exists, but the link count is now 2. So if I delete it, the link count becomes 1, and since it doesn't exist anywhere else, nobody is going to delete another time a C. That means forever it can sit as, the file can be existing without anybody noticing it. Okay. This is an example of garbage which is sitting there, which the blocks are allocated, it is not pointed to by anybody and it is still sitting there. Basically because I made a mistake because of the way things happened, the link count has increased, but there is no corresponding entry in the directory Y. Okay. So in a sense there is garbage being produced, and this is a safer situation because whoever was the right consumer of C got it and then disappeared, and there is no new consumer of C again, and it just stays as some blocks that are not cannot be returned to the pool again. That's all that happens. So now so this is less of a problem, and that's the reason why you will see that if you look at older file systems, they will go through step 1 followed by step 2. They do not go step 2 followed by step 1. This is what is called ordered write. Basically ensure that whatever happens, you first make sure that this part of the update to the storage system, that is the metadata corresponding to the inode corresponding to C, that is flushed to disk first, then later this is done. Okay. So this is what is called ordered write. You order the writes in which the things have to go to disk. Okay. Now the other methods, what is called logging, journaling and transactions, which are also used. So basically I just want to motivate the issue that if you are looking for some consistency of the file system information itself, you may have to do some management here. Okay. And that is done by many of these methods: ordered write, logging, journaling and transactions. Okay. So logging is a slightly more elaborate method to do the same. basically you make a note about the kind of changes that you're going to make in persistent store before you actually make the changes. It's also called journaling. And there is also something called transactions, which is basically, it has been popularized in the database community as basically equivalent to what you mentioned called ACID. That is, when you do certain things, some multiple activities together as one single transaction, you want to make it show that it satisfies ACID property. For example, in this case, you can say that both these two things can be taken as one single transaction, and if ACID property is present, then both of them either happen or none of them happen. Okay, so that also is possible. Okay, in the case of logging and journaling, what you do is you essentially can log this step that I'm going to do this followed by this, and then as you do it, you keep on essentially saying I finished part 1, I finished part 2, etc. If later I discover that I say part 1 is finished but not part 2, then I know that I already said I was going to do this, I am going to do what's called a redo operation. I know that 2 was not complete, I will go ahead and do 2. Okay, and this happens in the case of, typically file systems also usually do this kind of model. And the reason why is that is, it turns out if you have a power failure or crash, for example, or a panic, the system has to reboot. At reboot time, the file system can do some corrective action. Okay. For example, there is something called FSCK, etc., that can be used as a way to get control over the system with respect to its consistency. Okay. So that's what some models basically you redo the thing. That is, you already have made a note of what has to be done. You know that some parts have been completed, but some things don't have a record in the log saying it has been completed. Therefore, when you get back and you get control over the system, you basically redo it. Okay. So in some situations you can do it, and typically file systems follow the redo model of logging. There are some other situations where it turns out you really can't afford to have any inconsistency. Okay. And typically this is the case with concurrent transactions which have some real world implications, like for example monetary aspects, okay, transactions, database kind of things. Okay. So here basically you have to prevent inconsistency. Therefore, you do certain things and then you might undo things because it didn't satisfy some consistency properties. Okay. You don't wait for system to reboot before you do it. You have to do it. If there is inconsistency, you have to immediately correct it. Okay. So transactions and commit protocols are in this category. Okay. So again, just to reemphasize what I said previously, there are different ways you can look at consistency. You can do it at the level of system level like file systems do, or you can do it at the application level, because application level has given you some information about what kind of things it expects to be invariant, and therefore databases or those kind of systems, they can actually do application level model of consistency. Okay. So I hope I motivated why this consistency management also is important in single site storage systems, basically because they are essentially multiple components, and so they are essentially similar to, in principle, to what happens in multi-site storage systems. So we look at the consistency management in a multi-site storage system. We will first start with some simple models, then we go to slightly more involved models. Okay. And so what we will do is we will look at commit protocols first. As I mentioned earlier, commit protocols are used in those systems in which persistence is an important aspect. For example, file systems and databases, because when they fail, when some of the components fail, they usually have accumulated some state about what they were doing, and then when they recover, they have to use that information to somehow make the system again consistent. Okay. And we mentioned also that there are consensus kind of protocols where you don't really try to recover from if something has failed, you proceed. You basically proceed because there are some real time or other reasons why you cannot wait for some sites to come up, okay, as we discussed last time. So now we will talk about storage systems which each component has some component which each component has some persistent state that has been accumulated. Later we will discuss what is called group communication systems, which are used also in storage systems, so that a consistent view of the system is maintained when you send messages and the messages can be received or lost. Okay. That one is closer to the consistency kind of model. We will look at that also. So now we will start with the commit protocols. There are many types of commit protocols. We will start with the two-phase commit protocol. There is also a three-phase commit, and there are also other kinds of commit protocols. For example, Paxos is another one. We will look at some of those ones later. Okay. So what is involved in a two-phase commit? You have what are called, you have transactions which are executed in a distributed fashion. That means that it is executed not only at the coordinator, we will call it CFI. CFI is the coordinator, and it is also executed at multiple other places. The idea is that if there is any, let us say, if the transaction is to be completed, it has to be completed and agreed to upon by everybody else, or nobody should proceed with the transaction, any subcomponent of the transaction. Okay. So we will assume the transaction T is initiated at site SI, and the coordinator there is CFI. Okay. Now what happens is that the transaction coordinator sends information to all the other parties, saying that you have this small sub part to be done, and please do it. Once you are done, tell me when you are done. So that is what happens when all the other sites have completed their part of the work. They inform the coordinator saying that they finished that sub transaction that they were expected to do. Now once all the sites have informed the coordinator, we now start the two-phase protocol, okay? Two-phase commit protocol. Okay. So our idea now is that we asked each site to do some piece of this transaction. Okay. Either all of the effects of this should be persistently, let us say, made taken into account, or none of them should be. Because if we are talking about an asset property, it should be atomic. Either all of them do it or none of them do it. Okay. And so basically this protocol is all about that part. Okay. So what is in the first phase? The coordinator has got all the information from all the sites saying that they have done their work that was assigned to them, but they have not committed it to stable storage. They are not committed it. They are basically kept, they finished the work, they kept it in volatile storage, and once the commit happens, then they will actually update it to stable storage. Okay. That is the basic idea. So what is the issue here? Basically, the coordinator now says prepare T. He is trying to tell everybody, now be prepared to commit. I've got all information from all of you. I want you to be ready for the commit part of the protocol. So I will ask you to prepare. And CI basically what it does is, it logs prepare T and flushes it to disk, again stable storage. And then it sends prepare T to all CFK. Notice the way it is ordering it. First it logs it, flushes to disk, then only sends a message. Again, it is not done in the reverse order. You do not send a message followed by this. Again, if you do that, you get into you will essentially get all inconsistent results. So basically, you have to prepare T, flush it to disk, make it stable, then you send a message. Okay. CFK on receiving the message, prepare message, now it has done its sub transaction sometime in the past. Okay. Now it decides that either it can commit or not commit. Okay. For example, you try to get a hotel booking, the hotel booking did not work out, therefore the whole transaction should be flushed, it should be not committed. So here is basically what it does is it says that I am not going to commit. Okay. So it basically says logs no T, again it will and sends abort T to CFI. Okay. If on the other hand this sub-transaction really was successful, it is ready to commit. Okay. So it says to signal that it is ready to commit, it says logs ready T. Okay. Says I am ready to commit in case the coordinator agrees to that, it has to be committed. Okay. It's a conditional thing, it is basically saying, but I am ready, that's all it says. With all changes to log onto stable storage. Again, because that, for example, the hotel reservation or whatever, you are going to log all of it to stable storage, because now the minute I say ready T, that means I am willing to carry out my portion of it. I am going to make it stick. To make sure it is sticking, I have to, whatever changes I have to make the transaction, sub-transaction go through, I have to commit to stable storage. Okay. And then it sends ready T to CFI. Again, I commit everything to stable storage, then only I send a message. Okay. I should not do it in the opposite direction. Okay. Again, notice the critical aspect of stable storage. And if you are a storage systems person, you notice that all of this depends on the fact that there is some magic called stable storage. How is the stable storage itself created is a big question. Okay. So, for the time being, in this commit protocol, we just assume there is somebody has given you stable storage. Because notice that a disk is by definition is not a stable storage. I can write to a disk and then it can fail, and it will, next time I read it, I may not get the result back. It's possible. Okay. So, a disk by itself is not a stable storage. So, if you want to make stable storage out of unreliable components like disks, you need to do something else. Okay. That itself requires, surprisingly, a recursive aspect of commit protocols. Okay. So, we will talk about it later. Okay. So, again, before just to recapitulate, in phase 1, what happens is that once all the subtrans have completed the work, the coordinator sends a prepare message to all of them, but then each site decides whether to commit or not commit, depending on the success or failure of its own subtransaction. And then if it is not successful, it is going to say no and sends an abort message. If it succeeds in its subtransaction, it says it's ready to proceed as long as the coordinator agrees to, as long as the coordinator says that everything is fine with respect to everybody else. Okay. And it sends a ready message. Now, in phase 2, CFI receives response system prepare message from all CK or timeout. Basically, it waits for some time. Because again, the reason why there is a timeout is because things can also fall apart as things are going on. So, CI receives response to prepare message from all CK, and if in case it is ready T from all, everybody says that their subtransaction succeeded, then you log commit T. Basically, what is the coordinator going? Coordinator got a message from everybody that everybody is okay with proceeding the main transaction. So, you log commit. So, the coordinator now logs commit T, and it sends that message to everybody else. And each party who gets it also log that message that it is commit. Otherwise, if it is not ready to from all, then there is some problem in the transaction. At least 1 or 2 people, at least more than 1 person, at least 1 person had a problem. So, you have to abort, and again the coordinator logs this and then flushes it to stable storage, and then it sends the fact that it's abort to everybody else, who in turn, once they receive the message, they will also flush it to storage. Okay. Now, you can see that there is so much flushing going to disk, precisely because you want to make it persistent. That is why you will notice that your throughput is going to be determined by your storage system, how fast it can persistently write something. Okay. And then once that is done, once each of these CKs get this, they again send an ACK back. When CI gets ACK from everybody, it basically says that the transaction is complete. Okay. So, you can see that a commit is got a lot of parts to it. It can fail at any point. It can fail just after the subtransaction has been given, before the preparity has been received, after preparity has been received, before this commit has been received some particular site or commit, or it can fail at any multiple places. The question is, how do you recover from each of these possibilities? Okay. Because you are logging most of these things, you always have some record of what happened, and you can finger the log of both the coordinator as well as of this, all the sites. You can figure out where exactly things broke down and try to see if you can fix it. Okay. So, again just one thing to note is that when a ready T is sent from a site, these are basically a promise by a site that will follow whatever the coordinator decides. Okay. That means that it's okay with him, it's just that if the coordinator says okay, then I'll proceed, other will not proceed. Okay. That's basically the idea. That's the ready T is here. Okay. So, what are the various issues? Again, we are assuming that the failures are detected by coordinator or sites reliably. Again, as I mentioned earlier, detecting if a particular node is dead or etc. is not a reliable thing in the first place. Okay. But we are, for the purpose of this protocol, we assume it is. Okay. So, now there are multiple possibilities, either the site can fail or the coordinator fails. Okay. Now, let us say we detect at the coordinator that a site SK fails. Okay. Now, before it sends ready T, if that site fails, it is equivalent to abort T. Basically, nothing has been done, he has not told me anything what happened. I have no idea what he has done, whether the hotel transaction, whether it succeeded or not. I assume that since the guy is not responding to me, I assume the whole transaction has to be dropped. That is what this is. If it is after, that means site SK, you will notice that it has got a ready T, okay, in its log. So, what it means is that it is it has done its sub transaction and it has is ready to commit as long as the coordinator says so. So, that means that it is possible for me to continue the two-phase commit protocol and basically wait for some response. So, we will figure out how that happens in this recovery procedure. Okay. So, that part of it is here. Okay. When I said after ready T, this part is here. So, we will come to that soon. Okay. So, at the site SK, what is the basic recovery procedure? Now, the simplest is if commit T is already present in the SK. If your commit T is present, that means that it has already received a message from the coordinator to commit, and therefore, it can all you have to do is to redo the transaction. Okay. Because it was waiting for the commit T, but it failed before it actually completed the transaction. Okay. Because notice that there is a ACK here, right? CR is ACK small. Okay. That's the thing is this was not received and it died before that. That's why we are talking about the situation. Okay. So, the commit is present, therefore, we just have to make sure that total transaction went through. Okay. That is what we are doing here. Okay. If on the other hand, abort is present, that means that total transaction did not go through at all. Therefore, you just have to undo whatever you had something in your, if you had made some temporary, let us say, markings about your total transaction, you basically undo all those things. Okay. If in case they were actually sitting in persistent memory. Okay. For example, temporary files and whatnot. Okay. You oftentimes when you do some things, you put stuff, those kind of things, you just get rid of all those things. If it's ready T, the case I am talking about here, okay, what we are talking about here, okay. If it's ready T, what happens? The thing is, I was ready to do it, but I don't know what really happened. So, I have to go back to the coordinator to find out really what happened. If CI up, okay, it's easy, you find out what the coordinator says. If the coordinator says that please go ahead and complete it or just drop it, okay, you do it appropriately. If unfortunately at the time when this site SK comes up, CI is also down, okay, you have to check with other nodes to see what really happened. So, you keep checking till somebody or CI himself comes up saying what the situation is. Okay. So there is a issue of waiting for somebody coming up, and that is why there is some aspect of blocking that is going on. We will come to that again when we talk about this coordinated failure. Okay. So, So you have to keep waiting till the situation becomes clear exactly whether somebody has already committed it, or so that you can make consistent. Basically, again, we are worried about consistency. That's why, depending on what other people say, you have to follow their orders. Okay. If in case there is nothing at all, then it's equivalent to not having to worry about doing anything. You just undo whatever temporary things that you've done in your site, okay, in case they happen to again persistent. Okay. That's what this is. So we took care of the situation with respect to a site failing. What about if a coordinator fails? Okay. If a coordinator fails, you check if any CK has committee. If any CK, any site has got committee, that means that the coordinator already has instructed that the transaction is going to go through. Therefore, it makes sense to committee everywhere. Okay. If in case there is not a single guy who has got committee, then it makes sense to abort it, because that means that the coordinator actually had not made up his mind what exactly had to be done, and aborting is a safe procedure. Okay. So basically, if any CK has abort, you just abort it, because, and if there is not a single CK which has ready, then also aborting is makes sense. Okay. Now the only issue which is the problem is if all the other guys have ready T, okay, but the problem is that we don't know what was CA thinking, okay, because CA also would have been doing some part of the transaction. It may have decided to abort itself, or it might have decided to commit if everybody else agrees. So because of that situation, you really have to block till CI recovers. Okay. So this is basically the blocking situation that people talk about when they say two-phase commit protocol is blocking. The reason is that everybody else is ready to commit, but the party who actually is trying to make the transaction commit as a whole, that party's state itself is not known. Because that state is not known, you have to wait till CFI recovers. If that recovers, then you can proceed, otherwise you can't proceed. So normally it is generally believed that these situations are a bit rare. That's why most systems still use two-phase commit. If this is often, then it's a very bad situation. For example, suppose there is some kind of database system, it has got multiple sites, and the coordinator fails, and the system cannot come up for 2 days at a time, for example, or 1 day. Then it turns out that not only this transaction, other transactions which are connected with also maybe have to hang till that particular site comes up. So this is considered a problematic thing in those kinds of situations, but often it's not that bad. Therefore, most people often use two-phase commit. When it comes to network failures, you can map some of the failures to site or coordination failure. For example, if coordinator and some sites in one partition, we can say that other sites are essentially down. You can just map it that way and proceed with as we have done. Other sites which do not have the coordinator in their partition, they can assume coordination has failed, coordinator has failed, and so they can do recovery in whatever they want. Okay. So essentially, this particular protocol is correct but not live. Okay. It doesn't guarantee liveness, it guarantees correctness. And that is the case with almost all the protocols we will talk about for some time, because three-phase commit plus back source, all those things have the same issue, because correctness is far more important than liveness in some of these cases. Whereas when we talk about other systems on the web, for example, we can do with some amount of inconsistency. So their availability is more important. Okay. Here the idea is to keep waiting till the coordinator somebody comes up, till the situation becomes clear. For optimization, there are some optimizations people often do. Sometimes you have to, when you are doing some operations, updating some things, you need to take certain logs, and you actually log the set of logs also held, so that other transactions may need that same thing, same logs for the same data, you are able to figure out by looking at the log. Okay. So, if other transactions, they can get going, they do not use log cell by those which are hanging still. Okay. If you don't use logs, then in principle that hanging transaction could be holding on to some logs and you have to wait till that coordinator comes up. Okay. So, there are most often people do this. Okay. So, this is a way in which the blocking aspect, even if it is problematic, does not really bother you too much. There is another optimization for read-only transactions. Okay. Basically, because you are not updating anything, so you can send the fact that a sub transaction which does only read only, right? Basically, it can send read only transaction rather than ready T. Therefore, CI does not need to send commit T because there's nothing has to be updated. Okay, that also is possible. Okay, so there are some. So this is one way in which you can manage consistency across multiple sites. And notice that this is the same thing that a clustered file system also has to do. Okay? If you're talking about a clustered file system, clustered database, you have to do almost exactly the same thing, because if correctness is important, you have to do exactly these steps. Okay. Now let's look at three-phase commit. In three-phase commit, the idea basically is you have this blocking situation, you want to see if you can avoid the blocking. Okay. Now even three-phase commit, because of the fundamental aspect of the theorems we looked at, right? For example, FLP result, etc. There is no way to actually have no blocking. Essentially, either you, if you're looking for consistency, it will not be live. That's basically the issue. So even this has also the same issue. Okay. Here, what we assume is that sites can fail, but we'll assume that there's no network partition. Okay. So what we assume is that at most k sites can fail and at least k plus 1 sites up. Okay. That should be making assumptions. That means in some sense we are talking about a majority, we have a majority of sites that are up. Okay. So the basic idea here is, since we were blocking in the previous protocol because you couldn't read the mind of the coordinator. Okay. The coordinator did something, but did not divulge what he was planning to do to others, right? And therefore, everybody got stuck. Idea here is it possible that if T also, the coordinator, sends information about its particular aspect to other parties, then they can actually do something interesting. That is called a pre-commit phase. So we'll see how it does it. Again, we assume failures are detected by coordinators or sites reliably. In phase 1, the same as two-phase commit. What is involved here? Basically requesting each site to respond, and each site responds by saying whether they're ready or they're going to abort. Okay. Okay. So CI receives responses to prepare message from all CK or timeout. Any site abort T or no response from site until timeout, we abort it. We send abort to everybody. Ready T from every site. Now, this is a time when the coordinator sends a pre-commit to log and to each site to its log. Basically, in a sense, you are communicating to everybody saying that everything seems clear, I'm going to commit. Okay. So everybody knows about the fact that what coordinator's intentions are. Okay. ACK sent a coordinate from each site whether abort or pre-commit. Okay. So basically, you send it to everybody, and then the ACK is received from every site whether they got this message whether abort or pre-commit, and these things are also logged on their systems. Okay. So in case, see if here the coordinator may decide to go to pre-commit or may not decide to go to pre-commit. If he decided not to go to pre-commit, that means that he is not going to go through the transaction. Okay. If he has set pre-commit, that means that he is expecting further progress in the transaction, and that is what the phase 3 is about. Okay. Only executed with pre-commit in phase 2. Coordinator waits till at least k acknowledgements. So basically, as I mentioned, at least k plus 1 is basically waiting for a majority of acts. I think it should be k plus 1 here. It should be k plus 1, at least k plus 1 acts, sorry. So it waits till the majority number of acts, and then it logs commit T and sends it to each log. Notice that the parties already have some idea about what the coordinator was thinking about. Okay. That is why if there are some failure situations where they can actually, once they see pre-commit, they know that they can proceed, and we will come to exactly these exact situations. So what is the meaning of ready T here? Again, just like the 2-phase commit, it is site's promise to follow coordinator's decision. So in the 2-phase commit, it was one-sided. It was only the site's promises to follow coordinator. There was not a reverse one from the coordinator to the sites. When you say pre-commit, it is a reverse kind of handshake. Okay, your coordinator is promising to commit. Okay, so there is some additional state that has been generated and which helps you to resolve the issue in some cases. But again, because of all the results we have seen, theoretical results, this will also should block in some cases. Okay, there is no magic here. It is just that it takes care of some situation. Basically, I have more extra information. That extra information can be used to resolve some cases. That is basically all we can do. Now let us look at what this is. Okay. A site escape fails before ready T. Okay. And this is similar to the previous situation. Nothing really seriously has happened. Therefore, you can assume abort. Now it can be after T, we continue 3-phase commit. Again, we will come to the recovery part of it here. Okay. Again, this part of it is this ready or commit and pre-commit, these 3 situations. Okay. This, and this. Okay. So either we have abort or so if it is abort, it is basically you have to kill the transaction. If either one of these things, we have to figure out how to handle it. Okay. So what happens in this is very clear. If SK has commit T, that means that there must have been a message from the coordinator saying commit. Therefore, it is quite safe to do redo T. If it is abort, as you mentioned before, you basically undo. If it is ready T, okay, and there is no abort or pre-commit. Now, you don't know really what happened. So basically, you have to consult C of I to find T status. If Ci is up, it is easy. If Ci says abort T, then undo T. Okay. Basically, Ci is up. It turned out somebody else was not able to proceed with that part of the transaction. Therefore, we decided abort. But our site failed before it got the message. Okay, or whatever happened. Okay. That is why, as long as Ci says abort, you can just go and undo T. If it is pre-commit T, okay, basically Ci says, I just have done pre-commit, I have not proceeded further, I have not got response from everybody else. Okay. Then Sk, basically it is ready, so it can actually say, okay, you are still stuck at the pre-commit stage, I am anyway still ready, so I can proceed. So I will say I am going to send back saying I am ready to proceed if you are ready to proceed, the coordinator is ready to proceed. That is what this is. Okay. On the other hand, if Ci says, I have already said it is commit, right, then all I have to do is redo ready T, right. Basically what happened was that notice that you have sent a pre-commit, that is Ci essentially sent a pre-commit to everybody, but this was not seen by this site Sk, but since the protocol for reasons of liveness it waits only for, it assumes that at least k plus 1 guys are up. So because of this, our site, say, did not get those messages, but other guys got it, and then the site, the coordinator has actually gone ahead and committed it, not waiting for this guy to come up, sk. Okay. So that's why you can do redo of t, because it has been committed by the coordinator, and coordinator is saying so. Our problem here is, if Ci goes down, that means that this site sk has failed, and then you came up, you try to do something with, try to discover the state of CFI, the coordinator, but then CFI itself is down. So this is a situation where there is no further information. I have to really do something further. Again, this is an example where I cannot proceed till I do something else. Okay. So in here part of it, in execute coordinator failure protocol, what we do is we try to elect a new coordinator. Again, the 3-phase commit protocol, it tries to keep the system moving forward. So if the coordinator is dead, right, because coordinator already had sent information about the pre-commit, etc. Now I have to do what I have to proceed. Okay. So we have to get a new guy, and then we will see whether he can make the protocol move forward. That's the attempt here. If you find that at SK there is a pre-commit, but there is no abort or commit, again you have to consult CFI to find T status. We will come to this one, we will discuss it in more detail. Basically, it is exactly the same as here. Okay, you have to do the same thing up. Okay, so you have a pre-commit. That means that the coordinator promised to go ahead. Okay, but before that happened, right, your machine crashed, and you are trying to figure out if what really has happened to the T. Okay. So this coordinator failure protocol is triggered when a site does not get response from coordinator. Okay. So what we do is we elect a new leader, and then this new leader requests status of T from each site. Okay. Whether it is committed, aborted, ready, pre-committed, or nothing has happened. So if even one or more guys have committed, that means that it actually was committed in the past, so you can go ahead and commit it. If one or more guys says abort, then you have to abort it. If there are no aborts, or at least one pre-commit, this is a case where it's an interesting case. If 0 abort, but at least one pre-commit. Okay. Now CNew has to resume protocol by sending new pre-commit. Now you really can't go ahead and say commit, okay, because you have to see what CNew itself has. You really can't do commit right away, because if that happens, then you essentially get to the same situation as 2-phase commit. Okay. So what happens is that you know that the previous coordinator was planning to move forward in terms of transaction. That's what that 1 plus pre-commit says. But before it could be done, there was a failure and the coordinator failed, right? Therefore, the right thing to do is to try to move forward, and the way you move forward is by sending a pre-commit just as the previous coordinator did when he had decided almost to proceed, right? Now the reason why you need to do this is because if you don't do this pre-commit, then you can get into the blocking situation if CNew fails. Okay. So for this reason, you actually restart from where the pre-commit phase, and then try to make sure it proceeds. Okay. So this essentially gives you a way of making forward progress. is not exactly the same as the previous situation, but what happens is that we have to do this electing a new leader. Every new leader goes through the same phase, and this can keep on continuing. Okay. So, because it can keep on continuing, essentially there are no guarantees about liveness here also. Okay. So, actually there is one more scenario where no active site has pre-commit, and here it turns out abort the transaction is good. Actually there are 3 cases. The coordinator aborts for failure, it is very clear that you can abort it. CI has not reached precision, it is very clear you have to abort it. It cannot commit for failure. Actually it turns okay. It cannot commit before failure. You can show that it is not possible, because if you assume that CI has committed, then at least more than k pre-commit from site, right, that has to come in, and the new coordinator sees those things, and since the new coordinator sees it, pre-commit must have already been there, but I am saying that no active site has contradiction. Therefore, abort is quite safe in this case also. Okay. The one reason why I assume that no new network partition is because it turns out if I do not assume this, there can be multiple coordinators also. Okay. That also has to be avoided. So, in the next class what we will do is we will look at Paxos, which also resolves the same issues in a slightly different manner. Okay.